Welcome back. In the last segment, we were discussing how we update the constraints. Given the constraint, we can find how the probability distribution changes, how rho changes. But now we would like, in order to have a fully dynamical theory, we would like to be able to update the constraints themselves. And we figured out how to do that. We saw that if you impose that the Lie derivative of the symplectic form be conserved, then that leads to Hamiltonian flows, which take the form in terms of a Hamiltonian functional of Hamilton's equations. And this is how that looks like. You update the constraints, it's the second equation, by taking the derivative of h with respect to rho. Very good. So we solved the problem of how you update the constraint. And you might, and we almost have an expression for h tilde. It was the one that is such that the first Hamilton equation gives the continuity equation. So this part is totally under control. This one, we made a fair amount of progress, but there is a problem in that there was that integration constant in the Hamiltonian function h tilde that we had not figured out. So what is that? The way we're going to solve and figure out what is that extra dependence that appears in the Hamiltonian is by imposing additional symmetries. We're going to come up with a metric tensor. So introduce a metric tensor G for the embedding cotangent bundle, for the embedding space, and then impose that whatever flows you're going to consider, we want to know about those flows that preserve the metric tensor. And so what are the conditions that we can get from this symmetry? And what we're going to find is that by imposing both the preservation of the symplectic structure and of the metric structure, we're going to get the final piece of the puzzle. We're going to derive that. However, we're going to introduce this G by requiring, and this is the crucial element, that the space, the cotangent bundle, be spherically symmetric. So let us recall how that came about. Recall, for finite dimensions, for the simplex, we were dealing with a spherically symmetric space, 2n dimensions, cotangent space. And what we had here was a metric, a length element, given by, well, here you have a function of the normalization, then we have the sum of the delta thetas, and all of this goes squared, plus another function of the normalization, and then a sum over the delta thetas squared, plus 2 theta delta pi I squared. Very good. So this metric was a metric that generalized the information metric of the simplex S n minus 1, which is just this piece and that piece, and it generalized it by adding that extra part. So what we would like to be able to do here is do exactly the same thing for this infinite dimensional simplex. And so we're going to write the metric as a function times an integral of the delta rows plus a function times an integral of delta rows and delta phi's. And so this is what we're going to do. We extend the metric of the spherically symmetric simplex, in this case P space P, to a spherically symmetric, let me write it just as the embedding one, to a spherically symmetric phase space here, cotangent bundle. And the answer is going to be the following. The line element in this infinite dimensional space is going to be a function of the normalization and then an integral of the delta rho x's, and all of this squared plus a function of the normalization and then an integral. And here we have h2 rho x delta, I'll explain the h bar in a second, plus 2 rho x over h delta phi x squared. In this particular case, there were no h's. These pi's are these angles that appeared, these pseudo-polar coordinates that we introduced in order to make this a spherically symmetric metric. Here, the quantities that would be the angles are actually the little phi's we had before, and the delta phi would be, you might recall that the capital phi was h phi. I introduced, I just scaled it so as to make it look more like the physics of the Hamilton-Jacobi equation. It wasn't necessary. We could have kept the little phi's all throughout. But if this scaling is correct, then the delta phi that would appear there would be a delta phi divided by h. This is squared, and so here we have delta phi squared divided by h squared. What I have done here is I have removed one of those h's outside, and I have absorbed it into this constant, which is completely irrelevant as it was before. It's just a matter of choosing units. And so that's why there appears another h here in order to make it more or less symmetrical. So as you see, the introduction of the h's there is just a matter of, purely a matter of convention. Had people invented quantum mechanics using this approach back in 1927, the location of the h's would have been completely different. There would not have been any h's here. But you'll see how the h's end up showing up in other places. You say, but that's not really a necessary place. It's just conventional. Very good. Very good. So, but this is the metric for the embedding space, the cotangent bundle T star P plus 1. We want the metric for phase space. What this means is that, the metric here is for probabilities that are not normalized. We want to be able to normalize them, so we need to impose normalization. When we do that, the first piece here disappears. Furthermore, recall how the normalization constraint, the n constraint, or rather the n functional, induces a flow. And the flow said that when we write it like in terms of probabilities, the flow says that the coordinates at the point at one point get shifted by a formula like this. The shift of the probabilities is 0, and the shift of these phase fields of the canonically conjugate momenta get shifted by a constant. So you have these curves in which the momentum gets shifted by a constant. It's independent of x. And the way we interpret the action of the normalization constraint is that up here, rows are not normalized. When we eliminate one of these rows by imposing normalization, we must also eliminate the corresponding momentum. And the way we do it is by saying that all of these momenta here that lie on this trajectory, on this gauge orbit, are equivalent. So we eliminate 1 degree of freedom probability by imposing normalization. We eliminate 1 momentum degree of freedom by declaring that all those momenta on the same ray, on the same gauge orbit, are equivalent. So that's what the normalization does. So how do we go from this metric in the embedding space to the metric for the epistemic phase space that we want, the cotangent bundle of P? We do the following. We say, since all these momenta phi are equivalent, we would like to be able to say you have these rays of equivalent momenta, you have another ray of equivalent momenta, figure out which of those other equivalent momentum is the closest. Define the metric for this cotangent bundle as being the minimum when in this equation you minimize by varying over the change in nu that would appear here. And the result is B of 1, because if you set rho equals to 1, that's what you have there. But we're going to just forget this constant, rho. Then we have h over 2 rho x d rho x squared plus 2 rho x over h. And here we have exactly the same thing we had before, phi x minus the expected value of phi x all squared. And this metric is the Fubini study metric. As I said earlier, discovered by these guys, Fubini, and study back in 1905, 1906, way before people were doing quantum mechanics. Very good. Because all of these vectors that differ by these constants are going to be equivalent, it is a good idea to choose, instead of a whole array, choose a representative of the state of these points within the array, and we choose by using tangent gauge fixed vectors. In this particular case, tangent means you set rho equals to 1. Gauge fixed means you pick you set the rho equals to 1, which means that the sum of all the delta rows is actually equal to 0. And for gauge fixed, you pick the expected value of phi, which is the x rho x delta phi x. You pick that equal to 0. And that simplifies life tremendously. This guy disappears, so that the metric becomes, so then the metric on phase space becomes delta rho x squared divided, let me see, there is, yes, an h there, 2 rho x delta rho x squared plus 2 rho x over h, and here we have delta phi x squared. So that's the metric, and if we want to write this in terms of components, then this would become something like alpha x, beta x prime, delta x, alpha x, delta x, beta x prime, where this metric, and this is the crucial point in all of this, takes the form h over 2 rho x, 2 over h, 2 rho x over h, yes, and then zeros here, and the Kronecker delta that we had before now becomes a Dirac delta. This is the object that we're going to impose that its Lie derivative vanish. But before we do that, in order to make this very useful, we're going to realize that just like in the final case, now we can introduce a complex structure. The complex structure is going to be given by doing the following. We're going to invert the tensor, the metric tensor, so that we can raise the indices. So gamma x double prime, that's an index. Then we're going to have omega, and so here we're going to raise that index and have beta x prime. So raise that index with the inverse metric tensor, and the result is, it's just a matter of writing it down. This is not particularly enlightening. And then here there is going to be a 2 rho x over h, 0 with delta functions. And what is important about this metric tensor, this Where's the symplectic? Let me see. Yes, yes, yes. There is a minus sign. That's what I thought. There was supposed to be a minus sign. Is that if you take the square, alpha x, and then gamma x double prime, and then you do the square here by contracting there and doing the appropriate integrations. Beta x prime. This is going to be minus 1, 1, 0, 0 delta x prime. So you see that the square of j is minus 1, minus the identity. So you have a complex structure. I hope you appreciate the great advantage in being capable of using these indices here to replace all of these awful integrations that are all going all over the place just by repeated index summation. It's a very clever way to do it. There is absolutely nothing non-rigorous here. It's exactly, if you meant an integral, that's what it means. Yeah, this is an integral. But if you have a complex structure, nothing prevents you from not taking advantage of it and introducing complex coordinates. And the complex coordinates are going to be the square root of rho multiplied by I phase divided by h. So now this is another undesired place where h appears, and I just included it there for historical reasons. That's a place where h's appear. Clearly, if I had left the original drift potential alone, the little phi as being the momentum canonically conjugate to rho, then this would have been simpler. It's just one of those things. Very good. If I do that, the notation that I would like to introduce here is just like we did in the finite case. The notation, the index notation, is one in which I'm going to use a composite index with Greek letters from the middle. And in this case, these guys are going to be written as 1 or 2 as a function of x. And I'm going to call them size. And psi 1 is going to be exactly what I wrote up here. And for psi 2, I'm going to write the complex conjugate. But to make sure it is really the momentum canonically conjugate to psi, I have to include an I, and I have to include an H because of this. So now you start seeing where it is that many of the IHs that appear in combinations in quantum mechanics, where is it coming from? It's just a historically induced convention. So this is going to be the canonical coordinate from now on, and this is going to be the canonically conjugate momentum. When we do that, let me see. Yes, the normalization constraint takes the form obviously, and the rays or the gauge orbit, these are the states that are physically equivalent, are going to be a flow such that this is the wave function x. If you have the flow along or labeled by, parameterized by nu, this is going to be the wave function at the original point multiplied by this constant, and in this case the constant gets divided by h. So multiplication of the wave function by a phase factor does not lead to a new state. That comes from the normalization constraint. Very good. What is the corresponding metric? the metric that we got from information geometry and spherical symmetry. It takes a very simple form. The metric is minus 2i. The x, we have the change in the coordinate, and we have the change in the associated momentum. That's what it is. So now you see that this is real. There is an I, and then there is a minus I. So this is plus. So what this is going to be is going to be positive. So it's the only reason there is an I in front is precisely so that here we have the conjugate moment. If I were to write this in terms of metric components, that's what it will look like. And now the whole reason for this is that in this form, this metric tensor takes the following form. It's minus I 0, 1, 1, 0 delta Dirac delta. So why is this an interesting metric tensor? Well, it is actually a very interesting metric tensor because its components are independent. They're constants. They're just ones or i's or things like that. So their derivatives are going to vanish, and that means that the Lie derivative is going to be much simpler. The corresponding inverse, I don't need to write it, it's just flip the I to the minus I, and the metric, the complex form, complex structure tensor is going to be nu x prime is equal to, there is an I, a 0, 0, minus I, and then delta x prime. Exactly what we had previously in the discrete case, except that we get Dirac functions instead of Kronecker deltas. Very good. So now we're done. After all of this, I see you probably appreciate that really there is no thinking required. Once you got the finite case, going to the infinite dimensional case is more of the same. That's why I did the finite case before, because once you get used to what was the logic in that simpler situation, going to infinite dimensions is not really a complication. But now we're going to impose Hamilton killing flows. And so recall, if you have a flow that is Hamilton, you get Hamilton's equations, Poisson brackets, that whole canonical structure. If you now impose that the flow also preserve the metric, you get a killing flow. And the result of imposing both was that the Hamilton functionals, which are a function of psi and a functional of psi star, have to be linear in each one of these independently, and that forced it to be something that contained psi x, a kernel, which is really an infinite dimensional matrix, and then psi x complex conjugate. So forcing that both oh, I'm sorry, I did something wrong here, right? This is not this, that's not omega, that's G. Forcing that both the symplectic structure and the metric structure be conserved leads to quadratic Hamiltonian functions, which leads to equations of evolution which are given by Hamilton's equations. And that is going to be a linear. There is the 1 over IH there. So this is going to be 1 over IH, the integral of over x prime of k x prime psi x prime star. Here there is a prime missing. So you can see now that if you were to get the IH onto the other side, the evolution of the IH dd lambda is some kernel, some object here acting on the wave function. This again is a Schrödinger-like equation. Furthermore, we have that k is Hermitian, just as before. If you take the complex conjugate, this is supposed to be the transpose, and this guy is the Hamiltonian function is real. It's like an expected value of some kernel. So if this is Hermitian, this is going to be real, a real value. We're almost done. We have the conditions for figuring out what the Hamiltonian is going to be. If we want the evolution lambda, if we want the parameter to be time, then we need h, which is going to be a functional of these guys, to be quadratic in the wave functions, like that. But we also need this h. If we want lambda to be time, we would like the time, this is supposed to be an entropic dynamics, right? We would like the updating of the wave functions to be such that it is in agreement with the entropic updating of the probability, so that reproduces the continuity equation. So we want this h to be of the form we had before. Another way to say it is that if we, in entropic dynamics, the clock that we use to determine change, to determine time, is the system itself, is the probabilities. That is the clock that we're using. It would be desirable that the generator of time evolution uses the same clock. In other words, we would like this h tilde to reproduce the Hamiltonian that we had before for entropic dynamics. So how do we do that? Well, before we had written the Hamiltonian, you might recall. Let me rewrite what we had before. We had the integrand for the Hamiltonian was something like 1/2 rho MAB. Then there was a phi A, and then there was a dB phi minus AB. And this integrand is what we have to rewrite in a form that is linear in psi and in psi star, that is quadratic in these wave functions. in order to do that, I'm going to take advantage of an identity here. You can actually prove, this is just algebra, no thinking required, just roll up your sleeves and do the algebra. This is the same as h squared over 2m. The m appears in the form of the inverse mass tensor. Then there is a derivative of the wave function square, where these derivatives here, where there are this is a covariant derivative, is a derivative minus IH A, where A in configuration space, that component is H beta n AA x n. So here we have this derivative. Let me continue. Then we have dv. It's another one. And then we have the following form here. H squared over 8 rho squared m a b dA rho v a d b rho. Very interesting. So what this means is that whatever Hamiltonian we had before, we had to integrate this over dx to get the Hamiltonian. We can rewrite it in this form that looks much more like the Hamiltonians we get in quantum mechanics. And then we get this extra piece here, which is like a metric tensor and rows. This kind of expression may be familiar to some of you who have read about Bohmian mechanics. This is very similar to the quantum potential, but not the quantum potential as it arises in the Hamilton-Jacobi equation, but rather the quantum potential as it arises in the Hamiltonian. In any case, the Hamiltonian the Hamiltonian, which was originally written in terms of rho and phi, can be rewritten as a Hamiltonian that depends on psi and psi star. And what this is going to be dx. Now I'm just going to rewrite this term here. dA psi d b psi. And now there is this extra piece. Now this extra piece, as you may notice here, is just functions of rho. There is no phi floating around here. So the old f rho that we had before now becomes a new f prime with that additional piece. Very good. So this is our Hamiltonian. It may appear, the whole goal of all of this was to determine this f, right, this integration constant. And it may appear to you that we made no progress because we have replaced an f for an f prime. So now the problem becomes determine f prime. But if you look at this equation here, we also know that this h is supposed to be like quadratic in psi star. Here it is quadratic in psi star. This guy here is supposed to be quadratic in psi star, and independent of phi, where this f prime of rho is supposed to be quadratic. Let's write it like that, where I introduced a new kernel here. Let me write, here's the kernel, x prime. It's quadratic, and it is supposed to be independent of phi. So this condition, the fact that here you have this is x prime. You see this guy here includes phi x. This guy here includes phi x prime. It is not obvious that this phi x cancels that, but we have to make it cancel. Otherwise, we are not having a proper Hamilton killing flow. So we have an extra condition now that requires that the phase of this wave function and the phase of that wave function have to cancel. When we impose this functional derivative of phi vanishing, then what we get is that we get something like this. It's just an equation. You just have to work it out. Rho x 1/2, the integral dx prime, rho 1/2 x prime, and then here you're gonna get the imaginary part of the kernel, and then here minus I phi x minus phi x prime divided by h bar, and all this has to be equal to 0. So what I've just done is impose that this guy be quadratic and independent of phi. And the condition is this one. Now, this condition has to hold no matter how you start your evolution, right? It has to hold independently of what the initial conditions are. So it has to hold for all rows, must hold for all choices of row x prime. So what that means is that not only the integral has to vanish, but the integrand has to vanish too. And as I said, this has to work for all choices of initial condition. You can start your evolution with any wave function and it should work. That means all choices of the magnitude of the wave function and all choices of the phase and all choices of phi x and phi x prime. So how can you make this work for all choices of these phases? How can this vanish for any choice of these phases? The only way is if this kernel here happens to be local in X. In other words, this guy here is some function of X, and then there is a delta function. If there is a delta function, then the only place where this is not going to vanish is going to be, it makes one of these guys cancel the other, and so the dependence on phi disappears. So conclusion, the actual Hamiltonian which is a functional of these two guys, is going to be this integral that includes, here I'm doing an integration by parts, m a b dA dB plus a potential all acting on psi. And here I'm using the fact that this potential here, whatever it is, it doesn't include two arguments, it includes a delta function. That's why now in our Hamiltonian, instead of having two integrals, only has one. And this is the answer. We're done. Finished. If we do the Hamilton's equations, evolution, the equation for evolution of psi is going to be x, you do the Poisson bracket of this psi with the Hamiltonian. And this amounts to doing the Hamilton equation when you take the derivative with respect to the momentum. And the equation that you get from that, get the IH onto the other side, is the Schrödinger equation. Minus h squared over 2m, where m is written as the inverse mass tensor to covariant derivatives of psi plus v psi. We're done. Let me rewrite this in more conventional notation. Let me substitute the mass tensor there. If I were to write this in more the usual notation, this would look something like this. IH ddt of psi is equal to the sum over all the particles minus h squared over 2 mass, a Kronecker delta, which helps me figure out these derivatives, a n minus I beta n a xn, and then another one of these guys, d dx n b minus I beta n a b xn psi plus v psi. This tells us several things. T, which is introduced as this trick to keep track of the accumulation of changes, is the same as time, the object that is measured by clocks. Clocks, and in particular atomic clocks, are calibrated in such a way that what they measure is this T that appears here. So what we introduced as a clever inferential trick, as a clever device, parameter to see how changes of the probability distribution would accumulate, ends up being the stuff that's measured by clocks. So T is entropic time. It goes forward in time. Entropic time only evolves forward, and it leads to an equation, just a standard Schrödinger equation, which is time reversal invariant. T reversal invariance has been achieved Furthermore, the m's that appear here, we introduce the m's as being some clever trick, clever notation in a Lagrange multiplier. The multiplier had a dependence on particles, and so we replace the constant c sub n by a constant, an m that involved an n. And we had no idea what that was, just a constant. Well, now we see that the role that these m's play is the roles that mass plays in the Schrödinger equation. What that means is that whenever you have a device that measures mass, a mass spectroscope, or whatever other device you're using, the m that's being measured, the mn, which is something that came from the Lagrange multipliers, we have an alpha n, right? And we said whatever this is going to be, we're going to give it a name. We're going to put a delta t here. I don't remember now, maybe it was a delta cube. And then here we had something that just kept track of the units. Okay, this was just a clever choice. Let me see, is that the choice we used? I don't remember many times. Okay, mn. No, I'm sorry. There wasn't. It was h over m delta t. Yes, now I recall. The choice of Lagrange multipliers was such that there was a well-defined velocity, right? That made it proportional to delta t. And this, what was this? Just constants. But now we see that those constants are what, when you calibrate your scales to measure mass, those are the constants that are being measured. So this is what is measured as mass. So mass is also an epistemic concept. It's a Lagrange multiplier. Think about that. Betas. The betas appear in these covariant derivatives. Betas, if you put the right units, are given by that expression, where Qn is the electric charges, are the electric charges. So electric charges are also Lagrange multipliers. That's almost like obvious in this formalism, because after all, we introduced the betas as the Lagrange multiplier that calibrated a constraint on the displacement with respect to the external vector potential, like there, right? And so electric charges are Lagrange multipliers. So quantities in physics are kind of strange, as you see within this formalism. Quantities in physics are sort of like peculiar. Positions are real within this model. Positions are ontic. Everything else is epistemic. They're Lagrange multipliers, probabilities, entropies, constraints, the phases, right? These potentials. Everything else is epistemic. Quantum mechanics is a theory for the evolution of probabilities. Everything is going to be epistemic, except these are probabilities rho of x, except the x. But the theory never tells you how the x's change. The theory tells you how the probabilities of the x's change. It's a very different way to think about physics. I do not tell you why the particle moves. I just tell you how the probability of where to find it changes. And I stop there. Quantum mechanics is a mechanics without a mechanism. It doesn't tell you what pushes the particles. It just tells you what pushes the probabilities. Very good. With this, we end the semester. Of course, this is not really the end of this theory. In all truth, it's just the beginning. Now we ought to be able to figure out well, doing the Dirac notation is like a triviality. Let me just write it out a little bit. But the Dirac notation then is going to be introduced as follows. If you have two of these wave functions, we're going to invent a scalar product by saying except for some constant there, this is going to be the wave function for one x, and then the momentum for the other. Yes, psi 1x, I h psi 1x. Then we're going to put here the matrix of G plus I omega. And then now here we're going to have the second wave function, 2x and IH psi 2x, with here, this one with primes. And if you substitute your G's and your H's there, you're going to get exactly what you expect. Complex conjugate psi 1, psi 2. So you get exactly the same you had before. So you can now proceed to use the standard stuff. But as I said, getting the Schrödinger equation and even being able to introduce a Dirac notation is not the end, it's the beginning. From here, you can try to go ahead and draw all sorts of conclusions about how do you interpret the superposition principle, how do you interpret time reversal invariance, how do you interpret the classical limit, the quantum measurement problem, and so on and so forth, all the way to quantum fields and hopefully someday gravity. But that's for some other course. See you then.